Okay, this is nuclear chemistry, the last unit, lesson 3. Today we're going to talk about the difference between fission and fusion and solving half-life word problems. So we've already talked about artificial transmutation, and we said that that's when you change a nucleus of one element into the nucleus of something else by bombarding it with a high energy particle. In nuclear fission, and I always remember this by fission division, we are going to split the nucleus of a very large atom into smaller pieces by bombarding it with a neutron. So in comes this neutron into uranium-235, which causes it to split into two other fragments. One is barium-141 and the other is krypton-92. And in the process it releases 3 neutrons. And then those neutrons go out and bombard 3 more uranium-235, and they all split and they each produce 3 neutrons. So now you have 9 neutrons, and they're going to find 9 other uranium-235 atoms to bombard. And this is the beginning of a chain reaction. When this happens, not only do you form the two products that we're really not interested in, but you form a whole lot of energy. One disadvantage of fission is thermal pollution because a lot of heat is involved. Now, how does that contrast to fusion? Fusion means to unite. And we are uniting 2 smaller nuclei into a heavier nucleus. And this is often done with tritium, which is an isotope of hydrogen, and deuterium, which is an isotope of hydrogen. And they fuse together and they form helium. In the process, a neutron is given off, because if you have 3,1H plus 2,1H, that's going to yield 4,2He, and you know that the mass has to be equal, so this is going to be 1, 0, N. In order for the mass and the charge to balance, we gave off a neutron, and we also produced a whole lot of energy. So for purposes of Regents Chem, you're always going to see fusion happening between different types of hydrogen nuclei forming helium. So fusion, you're always going to see different types of hydrogen atoms combining to create helium and a whole lot of energy. So fusion means to unite, where fission, division, you're starting with something large and splitting it up. Here's another example of just taking 2 hydrogen atoms to create a deuterium. And these are other examples right here. This is the one that we just looked at. You can have 2 deuteriums. This is also sometimes one that they put there, but most often they use the one forming helium. Now, what are some advantages of fusion? Well, first of all, you have lots of energy given off. There's no waste produced. And this happens naturally on the sun. However, it's not impossible, but it would be very costly for this reaction to take place on Earth. We need to overcome the need for extreme heat, because you need extreme heat in fusion, and we need to develop material strong enough to withstand the heat. So it's difficult to contain the nuclei in a small enough area where we can control the reaction. So right now, this is not, something that would be cost effective for us to pursue, but it would be great if we could, because it certainly produces a whole lot of energy. Now, as we said, energy is produced both as a product in fusion and fission, although there is more energy associated with fusion. Now, where does the energy come from? You know that we obey the law of conservation of mass and charge, and energy when we undergo these reactions. However, the total mass of the product is slightly less than the mass of the reactants. And that's because a small amount of that mass is actually converted to energy. And this is called mass defect. And we're not going to go into this in this class. We talk about it more in the upper level class. You might talk about it in physics as well. But this involves Einstein's famous equation of E equals mc squared, where your energy is equal to the mass times the speed of light. All right, half-life. Half-life is the amount of time it takes for 1/2 of a radioactive substance to decay. And radioactive decay occurs at a constant rate. It's not affected by temperature, pressure, concentration, rain, sleet, or snow. It doesn't matter. Decay happens at a constant rate. The only thing that can be determined is the number of unstable nuclei that will decay in a given amount of time. So this is what I referred to as half-life, the time it takes for half of the mass to decay. It's a very important concept in nuclear chemistry. We'll use table N to work through these problems because that gives you the half-life for each one. The shorter the half-life of an isotope, the less stable it is. So we use radioisotopes with very short half-lives in biomedical testing because they're unstable and they become small relatively short period of time, which is great because we don't want that stuff lingering in our body. The longer the half-life, the more stable something is. So carbon-14 is a radioactive isotope that's used in carbon dating to determine how old different fossils or bones are. And that's really important because it has a very long half-life. Now, here's where things get tricky. They are not on table T anymore. They took the nuclear equations off. You used to have one that said the number of half-lives, basically, the number of half-lives is equal to little t over big T, where little t was the time elapsed and big T was the half-life that you would get from table N. However, that's no longer there on the reference table. We could also calculate the fraction remaining by taking 1/2 and raising it to little t over big T, which is really your number of half-lives. Well, there's two things you can do. You can either try to memorize these equations, or you can think about it in a common sense fashion, which is what I'm hopefully going to try to convey to you. Most chromium atoms are stable, but chromium-51 is unstable with a half-life of 28 days. So we know in 28 days that whatever I'm starting with, 1/2 of it will be decayed. So T is equal to 28 days, or my half-life. It says, what fraction of a sample of chromium-151 will remain after 168 days? Well, the total time is 168 days. So the number of half-lives is 168 divided by 28. That's following this formula. The time elapsed, 168 days divided by the half-life, is equivalent to 6 half-lives. And then the fraction remaining would be 1/2, or 0.5, raised to the 6th power, which gives us a decimal, which if we change to a fraction is 1/64. Now, problem is we don't have these formulas anymore. So how can I solve the same problem without using any formulas? Well, I'm going to show you. You know the half-life is 28 days, and you know that your total time is 168. So you have to figure out how many half-lives took place. How many times did this thing decay in half again and again and again in that 168 days? So hopefully you can see intuitively that 168 divided by 28 is going to give us 6 half-lives. 6 half-lives. So now we need the fraction remaining. Well, let's assume that we started with 1 unit. It underwent 6 half-lives. So 1, half of 1 is 1/2. Each arrow is a half-life. Half of 1/2 is 1/4. After the second half-life, half of a quarter is 1/8. After the third half-life, half of 1/8 is a 16th. After the fourth half-life, half of a 16th is a 32nd. After the fifth half-life. And then after the sixth half-life, I'm left with 1/64. So notice I got to the same exact answer without using any equations. If a sample of CR51 has an original mass of 52 grams, what mass will remain after 168 days? Well, we said chromium-51 has a half-life of 28 days. And we just said that if we have 168 days divided by 28, that gave us 6 half-lives. So what mass will remain if I'm starting with 52 grams? So this is going to decay 6 times. Half of 52 is 26. Half of 26 is 13. Half of 13 is 6.5. Half of 6.5 is 3.25. So how many half-lives am I up to? 1, 2, 3, 4. Not quite there yet. Half of 3.25 is 1.625. And half of 1.625 is 0.8125. And this is grams we're talking about. And I underwent 6 half-lives. Okay. How much was present originally? So now they want to know how much should I start with if 75 milligrams remains after 168 days. Well, we know we're still dealing with the same substance, so we know it's 6 half-lives because it's the same time, 168 days, and each half-life is 28 days. This says, hint, calculate the number of half-lives that have passed and then use the fraction remaining. Well, we don't want fraction remaining. We already know what's remaining. We want to know what we started with. So if I have 0.75 milligrams, I'm going to double this because I want to know what I started with, which is 1.5 grams. Oops, this is milligrams. I'll leave the units out so we get to the end. And this is 3, 6, 12, 24. How many do I have? I have 1, 2, 3, 4. Still got 2 more to go. 5, 6. So 96 milligrams must be what I started with. It underwent 6 half-lives, which left me with 0.75. Okay, let's do a couple more practice problems. Which of the radioisotopes from table N has the longest half-life? Well, if you look at table N and you look up and down, you see some are in years, minutes, days, seconds, milliseconds. So the longest would be uranium-235 with a half-life of 4.49 times 10 to the 9th years. I didn't see anything bigger than this when I looked at it. Shortest would be calcium-37, and I recorded that as 182 ms, which is milliseconds. What mass of a 100-gram sample of carbon-14 will remain approximately after 23,000 years? First thing I want to do is find out, does C14 have a decay mode? And it absolutely does. It's 5715 years. So I have a half-life equal to 5715 years, and I know the total time. So the first thing I want to do is try to figure out how many half-lives took place. So 23,000 divided by 5715 years. And that gives me approximately 4 half-lives. You always want to round to a whole number. It has to be rounded to a whole number. So 4 half-lives. What I started with 100, they want to know what's going to be left. So first half-life 50. Second half-life would be make it down to 25. Third is 12.5. And fourth is going to be 6.25 grams after it underwent 4 half-lives. Okay, last problem. 1.25 grams of iodine-131, which has a half-life of 8.02 days. After 40.4 days, what was the mass of the original sample? We want to figure out how many half-lives took place. 40.4 days divided by the half-life of 8.02. And this should give me 4. And it does. So 4 half-lives. And what was the mass of the original sample? So we have 1.25 grams, 2.50, 5 grams, and 10 grams, and 20. So we've got 1, 2, 3, 4. So we wound up with 20 grams as the original sample. All right, and that ends lesson 3. Have a great weekend.